Okay, so this is the outline of chapter 32. So we will briefly describe the Gauss law for magnetic field because it is mostly similar to the Gauss law for the electric field and even more simple, even more simple because as I mentioned, we don't have magnetic monopole. We only have magnetic dipole. We cannot separate a dipole into north pole or south pole independently. They must appear together. So on the right side of the Gauss law for the magnetic version, it will be nothing but zero because you don't have enclosed magnetic monopole. So it will be zero. So it makes the Gauss law for magnetic field even more simple. Okay, so the next we talk about the induced magnetic field and the displacement current. Actually, we will add a term on the MPS law. In this textbook, we call it the Maxwell's law. But actually, in some of the other literature, we just mentioned the whole thing, the MPS law. But this textbook, in chapter 29, it tells you the MPS law only includes the enclosed current. But actually, it also includes the displacement current, which we will describe it here. And then later on, there is some hardcore physics. You can just regard it as listening to a story. Actually, this is quite abstract, quite complicated, hardcore physics. To be honest, I don't really know it well, so I just try to let you know something I know. Yeah. Okay, so here is about the Gauss law for magnetic field. Gauss law for magnetic field. Okay, so similar to the Gauss law for electric field, we have the Gaussian surface, but we integrate the magnetic field over the Gaussian surface, and then the right side will be nothing but zero. So this is the net flux for the magnetic field, and it will be always zero for any closed Gauss surface. Yeah. So contrast this with Gauss law for electric fields. We have this flux, and then it equals the Q enclosed over epsilon naught. Yeah, like this. Okay, so it also mentioned that if you have a magnet bar and then you try to break it into small pieces, then it will be NS, small magnetic dipole. You can never separate the north pole or south pole. So we don't have a magnetic monopole. We only have a zero on the right side. So this is nothing special. Okay, so next we jump to the induced magnetic field. So in chapter 29, when we learn the MPS law, it says the equation is like that. The line integral of B dot ds is actually mu naught I enclosed. Mu naught I enclosed, if you still remember. Okay, so a changing electric flux induced magnetic field B. Maxwell's law is like, this one is actually the same as this one. Mu naught is still the same, but here we have this term rather than the I enclosed. So this one is like epsilon naught times d phi e dt. D phi e dt. Actually, this is still similar to the one E dot ds. If you still remember the Faraday's law, it is like negative d phi b dt. So if you still remember the Faraday's law, it is like that. The derivative of the magnetic flux with respect to time is equal to the negative of the line integral of the MPS loop. Okay. Yeah, actually, it is similar to that. This is a derivative of the magnetic flux, but we have a negative sign here. But here we have the electric flux over a loop, and then we take the time derivative. So it is like if we have magnetic flux changing, there will be electromotive force. It will generate some E field. So here, if we have electric flux changing, then it will generate some magnetic field. Okay, so this is the Maxwell law in this textbook. Okay, so yeah, so related to the magnetic field induced along the closed loop to the changing electric flux through the loop. Okay, so here you can see this is a capacitor. This is a capacitor. So if it's just a DC source, then we will have a voltage difference across these two plates, and then it will generate the E field. It will generate the E field from the positive plate to the negative plate. If the voltage difference or the potential difference doesn't change, then the E field between the plate will be constant, will be uniform over the whole region, at least within this region. And if this I is time varying, which means that this electric field will also be time varying. So across maybe something like here, this cross section, something like that. If you assume the capacitor is a cylindrical shape, so the cross section is something like that. If the E field is time varying, then just say this is the MPS loop, then the electric flux across this area will also be time varying. And according to the Maxwell's law, this one is not zero, then there will be induced magnetic field. Yeah. So before, you cannot say the MPS law is incorrect, because at that time we don't assume we have time varying E field. So this term will be just nothing but zero. Will be nothing but zero. So at that time, this one is correct. We don't have a time varying electric field. But here, if we only have a time varying electric field, this Maxwell law will look like this. Okay, so here it says, charging a capacitor as an example of this sort of induction. We consider the charging of a parallel plate capacitor, which with circular plate. So this is a circular plate. The charge on the capacitor is being increased at a steady rate. So this I is increasing, which means that the potential difference or the accumulated charge on the plate will be increasing. And so the electric field between the plate will be also increasing. Okay, so then the electric field magnitude being the plate must also be increasing at a steady rate. So in this case, crossing this loop, the electric flux is increasing. So according to this equation, there will be magnetic field. Magnetic field generate something like this. Okay, so yeah, so here, the electric field is direct into the page, showing in this cross. Consider a circular loop through point 1. Point 1 is here, a loop that is concentric with the capacitor rate and has a radius smaller than the plate, which means this red circle, refer to this red circle, and has a radius smaller than the plate because the electric field through the loop is changing. The electric flux through this area is also changing. So according to the above equation, this changing electric flux induce a magnetic field around the loop. So there will be, there will be induced magnetic field. Okay, so here we try to compare the Maxwell's law and the Faraday's law. So it looks similar. This is a line integral of the magnetic field. This is a line integral of the electric field. So on the right side, it is the derivative of the electric flux. This is the derivative of the magnetic flux. So here we have a negative sign, but here we have a positive sign. And we don't have anything before this term. Maybe if you have multiple term, then you multiply it by capital N. But if it is only one term, then N equals 1. So it changed to this case. But here we have a constant, mu naught epsilon naught here. So this constant is very important. It's very important. This constant related to the speed of light, 光速. So they are similar but different in two ways. Mu naught epsilon naught appear for matching SI units. SI unit, yeah. In this sense, it is matching the SI unit, but actually, this is related to the speed of light. The speed of light c is actually 1 over square root of mu naught epsilon naught. We will repeat it in the next chapter. Actually, we will derive why it will be the speed of light. And actually, speed of light is approximately 2.997 92458 times 10 to the minus 8 meter per second. So most of the case, you only need to remember 3 times 10 to 8 meter per second is enough. But for modern physics, or maybe for something like the quantum mechanics or relativity, you probably need to use 2.998 times 10 to the 8th meter per second. This one is, yeah, you can check it on Wikipedia. Okay, so another point is the negative sign here. For the Faraday's law means the induced electric field is counterclockwise. This is done if the magnetic field direct into the page and is increasing. So you can see here. Here we assume there is electric flux pointing into the page for the Maxwell's law. So this is referred to the Maxwell's law. Suppose this is increasing. This is increasing. Assume E is increasing. Increasing, then of course this time is positive. This time is positive. Then according to the right-hand rule, because into the page is positive, you use your thumb pointing into the page, your thumb pointing into the page. So your forefinger, it will be in this direction, your forefingers. The forefingers will be in this direction. So this is the direction of positive. And this is the positive term, so the B field will be pointing to this direction. Of course, if E is decreasing, then the B field will pointing to the other way around. And for the Faraday's law, we assume the magnetic field is pointing into the page. And of course, we also assume it to be increasing. Okay, so here, using the right-hand rule, we know the thumb pointing into the page is positive, and then clockwise is positive. But here we have a negative sign here. Oh. Yeah. Okay, so just now we mentioned this part. Yeah, this part. I don't have. Yeah, so this cursor is quite small. Okay, so just now we mentioned if a magnetic field is increasing, the magnetic field is increasing. Yeah. So you use right-hand rule, you use your thumb pointing into the page. So clockwise will be the positive direction. Okay, so however, we have a negative sign here. So the induced E field will be counterclockwise. Here we have a clockwise magnetic field induced. So this is the second point difference between the Maxwell's law and the Faraday's law. They look similar, but they have some non-similar things. Okay, so here in chapter 29 we have the MPS law. And then in chapter 30 we have should be 32. In chapter 32 we have a Maxwell's law. Okay, so on the left side we also have the line integral of the B dot ds. But on the right side we have a mu naught enclosed, mu naught times I enclosed, and also mu naught epsilon naught times the derivative of the electric bus. So why not take both? So we add the right side together. So finally we will get, this is the static current enclosed by the MPS loop. This is another thing. So far we don't know what it is. But on the left side we have the line integral. So this one is a static current will generate induced magnetic field. Also, this is not induced magnetic. This is the magnetic field generated by the static current, and this is the induced magnetic field due to electric bus changing. And you can simply imagine that it is similar to the current of the capacitor. Because if there are current charging the capacitor, then there will be electric bus changing for the cross section. So you can regard it as the current of the capacitor, and in physics framework we call it the displacement current, which I will introduce a bit later. So here, this is called Maxwell's law, because just now we mentioned that for the upper one we call it MPS law. For the lower one is the Maxwell's law. So when we combine them together, it is Maxwell's law. It's just like the PPAP. When you combine the pen with the apple, it becomes apple pen, something like that. Yeah, so this is the Maxwell's law when there is a current but no change in electric bus, such as with a wire carrying constant current. The first term on the right side of the equation is 0, and vice versa. So it doesn't really matter, or we have two terms on the right side, which term we should take. When there is static current, then we will have the first term to be non-zero and the second term to be 0. And if there is no static current, if there is only electric bus changing, then the first term will be 0 and the second term will be non-zero. Maybe for some of the case there will be both, but it might be a more complicated situation. So we have to bring this two term on the right side for the whole Maxwell's law, or for some of the literature it only mentioned it as MPS law. Okay, so let's take a look at this sample problem. It says a parallel plate capacitor with circular plate of radius r is being charged. So derive the expression for the magnetic field at radius r for the case r is smaller or equal to capital R. Okay, so here, using the Maxwell's law, because we only have electric flux changing, so we only use the Maxwell's law. Actually, you can just write the whole MPS Maxwell's law, and then you will find that mu naught I enclosed is 0. So we can just write the line integral of b dot ds equals mu naught epsilon naught d by e dt. Okay, so similar as before, we have integration of b ds because they are parallel. And then this is mu naught epsilon naught by e. We assume the electric field is uniform between the plate. So this is nothing but d dt and then e times a, because originally phi e is the surface integration of e dot dA. This is not a closed integral because this is not a closed surface. This is not a closed surface. This surface is only bounded by the MPS loop, so this is not a closed surface. So if it is a constant, it is nothing but e times a. Okay, so next, BDS is nothing but b times 2 pi r because it is uniform, and then a is a constant. So we have mu naught epsilon naught a times dE dt. So the electric field changing. So so this a is actually a circle pi r square. So we have equals mu naught epsilon naught pi r square dE dt. And then finally, we find b to be b times 2 pi r, and then we can partly cancel this r with this r, and then pi with this pi. Okay, so finally we will have mu naught epsilon naught r over 2 times dE dt. Okay. Yeah. Yeah, so the part B, evaluate the electric field, the field magnitude B for R equals to capital R over 5, like this. Okay, so dE dt equals 1.5 times 10 to the 12th power. Okay, so we only need to plug in the values. B equals mu naught epsilon naught R over 2 times dE dt. Okay, so mu naught is 4 pi times 10 to minus 7. And then epsilon naught is 8.85 times 10 to minus 12. And then R is 11 times 10 to minus third power. And then all over 2 times this one. dE dt is 1.5 times 10 to the 12th power. So this is 9.18 times 10 to minus 8 Tesla. So for part C, find the expression when R is larger than capital R. So now the MPS loop is outside. Maybe I can draw it better using this one. Okay, like this, yeah. Okay, so here, we're still using the Maxwell's law, like this, mu naught epsilon naught d phi e dt. And then we're still using similar things, b times 2 pi r equals mu naught epsilon naught. So we should have phi e to be e times a. But here, the a is not the whole thing. It's not the whole thing. Maybe I can. Yeah. Actually, this This one only account for this one, not including the outside, not including this part, because there are no electric bus there. There are no electric bus there. No electric plus for the purple part. Okay, so this A should be only pi capital R squared. So up to here is capital R. And then we have the dE dt. So we can only cancel pi. We cannot cancel R because one is small, one is big. So finally, B equals mu naught epsilon naught R squared over 2R times dE dt. Okay. Okay, so this is it. Okay, so next we mentioned the displacement current. Displacement current. Because just now we have B dot ds equals, on the right side we have a mu naught I enclosed plus mu naught epsilon naught d phi e dt, like this. So when you consider the dimension or the SI units, this is the current, and then mu naught times something. So this term should also be a current, although this is not actually a current, but the dimension or the SI units is the same as the current. And here we call it the displacement current. 中文叫做位移电流。Displacement current. So if you compare the two terms on the right side of the equation, Maxwell's law, you will see that the product, this one must have the dimension of a current. In fact, that product has been treated as being a fictitious current. Fictitious 就是虚构嘛，虚构。Called the displacement current. Actually, this is a current through the capacitor. So we have ID equals this epsilon naught times the d phi e dt. Okay. And in that case, if we use ID enclosed to replace this one, we have ID enclosed here. So where ID enclosed is the displacement current encircled by the integration loop. Just now I mentioned that the displacement current is similar to the current of a capacitor. Let me show you why it looks like that. Starting from here, and we make the assumption as this is for parallel plate capacitor. For parallel plate capacitor, then we will have ID equals epsilon naught A dE dt, because just now we already have a phi e to be integration of E dot dA. Of course, we assume E and the area vector is parallel with each other. So E dot dA is nothing but EdA, and then E is uniform over the region of the parallel plate capacitor. So so E integration of E dot dA is nothing but E times A, and A is a constant. So we can put this A in the front, and then we only have dE dt. We only have dE dt. So it is E times A, like this. Okay, so next step is like we have a E not A. We try to divide it by D, and then we multiply it by D. So we have a D dt, E times D. Okay, so if you still remember, this is the capacitance of a parallel plate capacitor. So this is C. And then E times A, E times A, E times D, I mean, E times D. For the parallel plate, this is D, and then this is E. So V, the voltage difference, V between these two plates will be E times D. E will be E times D. So we have a dV dt here. And if you still remember, ID equals C dV dt is actually the current of the capacitor. Okay, so here we still talk about the displacement current. Yeah, so in chapter 29, we actually find the direction of the magnetic field by a real current I using the right-hand rule. We can apply the same rule, finding the direction of the induced magnetic field produced by the fictitious displacement current. Actually, the derivation will be actually the same. The only difference is that in chapter 29, it is about the practical current, the conventional current. But here, if we assume it is displacement current, then using the same thing. In chapter 29, we use B dot ds equals mu naught I enclosed. Here, what we only use here is B dot ds equals mu naught time ID enclosed. And then if we assume this one to be the same as this one, we will find the magnetic field generated by these two types of current to be the same. And you check back the derivation if you forgot. If you have already forgot, then you can check back the derivation in chapter 29. I do not repeat it again. Yeah. So which is similar to, yeah. If you still, you should remember this equation, although you don't necessarily need to remember it in the exam, but actually this one is appear many times. B equals mu naught I over 2 pi r for a long wire, and then the magnetic field generated at the point r from the wire will be this expression. And if it is a wire with the current, and then if you find the magnetic field inside the wire, then it will be something like proportional to the distance r, and then this r square is here. Okay, so I think I have already derived it before. Okay, here, let's see a sample problem. So the circular parallel plate capacitor is being charged with the current I. Between the plate, what is the magnitude of B dot D, line integral of B dot ds in terms of mu naught and I at a radius r equals capital R over 5 from their center? Okay, so here we have a B dot ds equals mu naught ID enclosed. And you can assume like that there will be the whole current for the capital R, and then now your concern is small r. Small r here is capital R over 5. So you only consider this part, which means that ID enclosed over ID D equals pi r square over pi capital R square. And then here, R equals capital R over 5 square pi R square. So it is 1 over 25. Okay, so we have ID enclosed equals 1/25 of ID. Okay, so we just plug in this one here. We have integration of a B dot ds equals 1/25 mu naught ID. Or simply I, because this I is the displacement current. So we can only write I for it. Okay, so this is the answer for this one. And then for part B, in terms of the maximum induced magnetic field, what is the magnitude of the magnetic field induced at this distance inside the capacitor? Okay, so here we have a BR equals mu naught ID over 2 pi R square times R. For R is smaller than capital R. This is actually proportional to R. Okay, so BR over B max. For the maximum case, of course, you take the capital R. So which means that a BR over B capital R. So which will be nothing but B 1/5 of, and then B R. So it will be nothing but 1/5. So BR is nothing but 1/5 of B max. Okay. Okay, so far, let's make a summary. So for the Maxwell equation, there are four fundamental equations of the, this is a four fundamental equation of the electromagnetism. Actually, there are some even more, but they are dependent to each other. So if we only have these four, then we can actually solve for almost every problem in the electromagnetism. Of course, maybe you learn some other laws or rules or theorem, then maybe your calculation will be faster. But the Maxwell equation is sufficient to solve for any problems. So we call it the Maxwell equation here because Maxwell tried to summarize all these four equations as the backbone of the electromagnetism. Although none of this law called the Maxwell's law. Maybe this one we have MPS Maxwell's law. Maxwell only apply here. So these four equations explain a diverse range of phenomena. They are the basis for the functioning of such electromagnetic devices. Yeah, so we have two Gauss law, one for electricity and one for magnetism. One Faraday's law, one MPS Maxwell's law. So the first two might be more easy because they refer to the electrostatic or magnetostatics. And the Faraday's law, MPS law might be a bit more difficult or maybe more complicated to understand because this one says the time-varying magnetic field will generate electric field. And time-varying electric field here will generate time-varying magnetic field. So, and time-varying magnetic field will go back to here and generate time-varying electric field again. So, this is the basic idea. how do we why do we have the electromagnetic wave 电磁波 okay so maybe today we stop here and try to let you know that